Okay, good. All right, so we are reaching the end of this whole week. And first of all, I would like to thank the organizers to be brave enough to organize this nice conference with the option to be here in person. This is the first conference I attend in a year and a half or more now, and it feels really good. So thank you for doing this. All right, so why are we here today, apart from enjoying being with each other? I like to show this figure here. This is on the y-axis the change in the number of papers on AstroPH as a function of time for different keywords. What you can see is that the fraction of papers dealing with stars and galaxies are roughly constant. You can see the gradual increase of planets due to exoplanets. And if to this we add the trend for neural network, this is how it looks like. Okay, and so I have looked at lots of keywords in the statistics of archive semantics. This is unprecedented in astronomy. There is no other trend like this in the past 20 years, so there is really something happening. Sometimes people ask, how does this compare to Bayesian statistics? Because we did hear a lot about Bayesian statistics some 10 years ago or so, and this is how it looks like. Okay, so it's, as you can see, they have been part of our tools, of the way we do data analysis, but it's a very different type of trend. So there is really something happening with machine learning and neural networks. So this week, we have heard about two types of tools, two types of approaches. On one hand, we've heard about dimensionality reduction techniques a la PCA. So we heard about self-organizing maps, t-SNE, UMAP, and others. Those techniques are well understood. We know how they work, and all the work that needs to be done is to understand, to interpret the results that we see. And as you might have seen, these techniques have not really been part of the debates that we had every day during the week. And so what I'm going to do during the rest of my talk is to focus on the other one, neural networks. This is really the key, and this is really what resonates with the title of this conference, which is Debating the Potential of ML in Astronomy. All the debates were about neural networks, how to understand them, what can they do for us, etc. So I'm going to basically focus on those for now. And because nobody has really said it during this week, I'm going to just mention a couple of words on why they are so good at so many tasks. So this is a diagram showing the two types of way we can interact with data. We can do analysis, going from lots of pixels to information, or we can go the other way around, and that's called synthesis, going from information to generate data. Most of us are typically interested in analysis. And so when we do analysis, we want to do two things. We want to use an estimator that's going to discard the irrelevant variation in the data and just keep what is informative. And so why are neural networks so good at this? Okay. And the key reason here, and that applies to all neural networks, is that they enable geometric stability. And in addition, what is possible to do is to plug in a given symmetry in them. So what do I mean by this? So the geometric stability, this is typically what we want if you want to do identification. If you have a cat in an image, you want to be able to distort the image in a number of ways and still recognize the cat, or you want the estimator to be able to still recognize the cat. And so that's a key property, and that's what neural networks bring to the table. And in addition, depending on the type of data we have, often we have invariances or symmetries, and that's often the case in physics, and we want to take them into account. So we have different types of data that belong to different domains. We can have data on pixels on a grid. We can have data on the sphere. We heard this week about data on graph, and we can have data on manifolds as well. So each of them comes with a given symmetry. We can have translation, rotation, permutation. So a graph is described by an adjacency matrix, which is going to be a matrix encoding for the links between different nodes. This matrix is invariant to permutations. Okay, so this is the type of symmetry that we want to have in a corresponding neural network. And so given the symmetry and the domain that we have, there will be an architecture that's going to encode these invariances. and that will be stable to geometric stability. And that's really the key that allows us to do all sorts of calculations, that allows us to manipulate data in new ways that were not reachable before. Okay, and I think that's why many of us are here in the room today. So this week we had a number of reviews, very interesting ones. Ben Vandel told us about cosmology. To be more specific, he told us about NPE, Borg, LFI, Delphi, SBI, IMNN, and if you could follow the talk all the way to this point, he even added SBI with moment and posterior marginal networks. Okay, so it's great to see the enthusiasm in that field, theoretical cosmology and how to infer parameters from cosmological simulations. Lots of new ideas, lots of new techniques that are popping up all the time. There's a lot going on in this field. This is very exciting. Next, we were supposed to hear from Elizabeth Krauss about machine learning and astronomical imaging, but instead, she decided to give us a talk on a review of the dark energy survey. So first, I was surprised, but then it became very, very interesting. The contrast between the two talks was quite insightful, because in Elizabeth's talk, basically, there was almost no machine learning. So on one hand, she was presenting to us the latest results of the latest cosmological survey. And we could, understand all the hard work that went into this, but very little ML contribution in this project. And so the contrast between the two talks, to me, was very interesting. And I think it links to one of the topics that were discussed this week, how to apply really ML to real data, and how can the community accept the results. So I think this is an interesting point here. We heard about interesting methods. Jill emphasized the use of GANs, variational autoencoders, and normalizing flows. Let's keep an eye on those. Lots of interesting things are happening. Paco presented his new simulations to us, told us that we now have available hundreds of terabytes, if you can download that amount of data, of simulations with dark matter, baryons, etc., that are fantastic training sets for all the machine learning techniques we can use. I learned a lot about exoplanets. This is not my field, but it was really interesting to see that in that field, machine learning is used mostly to describe the noise, which is complex, not so much the actual objects of study. And then radio astronomy and how machine learning can be useful to detect outliers, especially. So it's been an interesting week with plenty of excitements, lots of talks from young people, and we heard about all sorts of use of neural networks, how to use them for identification, classification, outlier detections, and so on. And I saw neural networks being thrown at lots of different kinds of problems. Absorption lines, galaxy spectra, galaxy morphology, large-scale structure, and so on and so on. So on one hand, that's very nice, but after a whole week, to me, something has been missing. After all these applications of ML, we have not really seen discoveries. Okay. And by this, I mean new phenomena, new astrophysical understanding. And I have noticed that some frequent words that came up during this meeting were LSST, Euclid, and Rubin. And many of the techniques that have been presented using real data rely on the hope that they will make a difference with these future surveys. And we have to be a bit careful here. So on one hand, we have this explosion of the number of papers, but the number of discoveries is not really following. And so why? Has machine learning improved our understanding of galaxy formation, AGN physics, and our understanding of the properties of the ISM? I don't really think so. At least I have not seen that. Why have we not discovered new physical trends, new scaling laws? There have been lots of studies of galaxy morphology, but have they led to any new galaxy physics so far? And I don't think so. I would like to just add a note that there is definitely progress in our understanding of how to do better inference in the context of cosmology, in the context of stellar spectroscopy. But this is mostly in the context of parameter inference. This is not yet at the stage where we are reaching new astrophysical understanding. So why? Why is the impact of ML so limited? You know, on one hand, we have great promise, but then at the end of the day, the actual impact is so limited. So I'm going to just mention two possible reasons. And the first one is that physics is about extracting the essence of a phenomena, and the typical use of a CNN doesn't really do that. Okay. And so what do I mean by this is that this is a typical use of a CNN. You start from lots of pixels, and the CNN, which is just function approximation and nothing else, is going to basically define this function such that it's going to match the labels that you have during training. But this does not lead to any simplicity and does not give you the essence. I do believe that years from now, we will have tools to query learned, trained CNNs in order to extract some of the structure that they have learned. But as of today, those tools are not really available. We have to create them. There is one way to go around this, is to use autoencoders, and we had a few talks about this. They were very interesting talks because they are the talks where we got the closest to the physics. Okay, by having a bottleneck, using a system like this, we can reduce the dimensionality in a nonlinear way, and we can have access to a few key dimensions or parameters that can be very close to the physics. So I think this is really the key. This is what should be done much more often in order to try to extract physics from data. And so, final word, perhaps our data is too simple. What do I mean by this? This is a sketch of a complexity axis along which I have organized some astronomical data, 1D and 2D. If we step back and if we consider the bigger picture of all data sets out there, we live at the very low end of the complexity axis in astronomy. Our data is way simpler than data you find in geophysics with remote sensing, for example, and that's way simpler than all the natural images and the cats and dogs that ML techniques are almost designed for, in a way. I would like to use one example, using a slide from Sihao Cheng's talk. He did an experiment where he tried to infer cosmological parameters from lensing simulations. He did that with a number of techniques. One was the state-of-the-art CNN that led to a Nature paper. And he used other techniques, including the one called the scattering transform, which is very interesting, and I learned a lot from it. What he showed is that the scattering transform here, which is a mathematical neural network which has no training and just 2 layers, performs as well as the state-of-the-art CNN, which in this case has about 1 million coefficients. So we heard about the challenges of understanding what neural networks do and when we talked about interpretability, what to do when we have 1 million parameters. But this is an example showing that, in fact, even though you get great results with 1 million coefficients or parameters, actually the system is much simpler. You can extract as much information with just 30 coefficients. It doesn't apply only to weak lensing, as Sihao showed. This is valid in general for physical fields. You have 5 physical fields here. We can play the same game. We can extract these coefficients, and from these coefficients, we can regenerate new fields, okay, new texture. And this is showing you that it works well in all these cases. And so those physical fields, they are not as complex as you might think. You don't need millions of coefficients to analyze them, to interact with them. And so going back to my complexity axis here, my message is that in astronomy, we are really at the low end of this axis. And perhaps we don't always need the tools and the many layer CNNs that are used in other contexts to detect cats and dogs, for example. All right, so this is my conclusion. I would still like to end on a positive note. I think it's an exciting time. We are witnesses this machine learning revolution, which is, to me, a new way of thinking, and I think personally that's the great outcome. It's nice to see many new tools, many new ideas, many projects, and all sorts of things that were almost unreachable about 10 years ago. And as I said, personally, to me, the most gratifying thing here is that we now have new ways to think about data and to think about statistics, and that's really exciting. At the same time, we are in transition phase. Okay, there is great potential, but things are moving very fast, and we don't yet know exactly how to do things best. I think there are many signs with the talks we saw, with the discussions we had, showing that in 5-10 years, we are going to do astronomy in different ways. Exactly how, I don't know yet, but things are changing, and personally, I enjoy that. And I will finish with just this sentence. Let's still keep in mind that there is a bit of an offset between the promise of ML and what the rest of the community is expecting from us and what they want to see from us. So let's try to focus on this and show them that we can do great things. Thank you.
Thank you very much, Bruce.